Okay, now we know that abstract algebra is useful in the technology of cryptography, which is the creating and sending of secret messages. And in this section, we'll look at a different application called Diffie-Hellman key exchange. So this is one particular technique used in cryptography. So let's go back over some terminology. Cryptography uses keys. There are several types of keys. A public key is known to everybody. It's not secret. It's typically used for encrypting messages, although we'll see later, sometimes it's used for decryption in a certain particular application. Now, if a public key is going to work, you need to have a matching private key that someone can use to decrypt the message encrypted by the public key. So the private key is known only to the receiver. Even the person who sends the message may not know the private key. In some cases, there's a key known to both sender and receiver that's called a symmetric key. So only those two people know the symmetric key, and they both use it to send and receive messages. So one scenario you can have in cryptography is you have two people, and they want to set up a symmetric key, but they don't have one yet. Now, suppose the only way they have to communicate is over the internet. Then how are they going to send a symmetric key? Because the symmetric key has to be secret. And if you send over the internet, that's not secret information. So you need some way to set up a symmetric key if you're going to use a symmetric key for secret communication. And that's what Diffie-Hellman key exchange does. It's a way to set up a secret key over a channel or communications link that's not secret. It seems like magic, but you're able to do it. So here's the procedure. And as I said, it uses modular arithmetic. So the two parties who are communicating are Moses and Rachel, and they agree on a pair of numbers P and G. P is called the modulus, and G is called the base. These numbers are not secret. So the whole world can know what these numbers are. So in practice, these numbers have certain properties. We won't talk about that right now because this procedure works for any values of P and G that you choose. Okay. So Moses chooses a secret integer n, which is known only to himself. We could call that Moses' secret key. He then computes Q, where Q involves raising the base G to the nth power and taking it mod P. So that's how Moses computes this Q, which he then sends to Rachel. So again, Q is public knowledge because he's sending it over the internet. We can't assume that that's secret because people may be eavesdropping. Now, even Rachel does not know Moses' value of n. She only knows the Q, which is obtained by raising G to the nth power and taking it mod P. Now, you might think she could find n easily using this information because she knows G, n, and P, but in fact, it's not so easy. And we'll see that later on. Now, Rachel also has her secret integer m, and she computes r, where r is equal to G to the nth power mod P. So Rachel's r is similar to Moses' q, but Rachel's using her own secret m instead of Moses' secret n. Okay. So you can see down in the picture here, this is what we have. Moses starts with n, he computes q, he sends q. Rachel starts with m, she computes r, she sends r. Right now, you might seem that nothing has happened because Rachel has her secret m, Moses has secret n, and neither one knows each other's secret. The magic comes when Moses takes this r that he gets from Rachel and raises it to the nth power, where n is his own secret key, and takes the result mod p. And Rachel does the same thing. She takes this q, which is public knowledge, raises it to m, which is her own secret, and takes the result mod p. So Moses gets this number km, and Rachel gets this number kr. All right, now what's the relation between km and kr? In fact, they turn out to be the very same number. And that's what this exercise is all about here. And you're asked to fill in the blanks to show that, in fact, this Km that Moses computes is the same as the Kr that Rachel computes. Now, this is quite amazing because the only information they sent, this Q and this R, this knowledge does not, this does not give you the values of N and M, but somehow they combine these two secret pieces of knowledge to create something that they share in common. So I should say that this whole procedure depends on the fact that even though someone knows Q, P, and G, it's difficult for them to find N. And even though someone may know R, P, and G, it's difficult for them to compute M. Because once someone computes M and N, then the game's up. The whole scheme works on the supposition that N and M are difficult to compute. And we'll see how that works out later on. All right, but at this point, we can see that somehow these two have exchanged information and they end up with the same result. Okay, so here's an example you can work. This is another example of with specific numbers. All right, so let's try to analyze what's going on. In both Moses and Rachel's case, they're taking this base G and raising it to a number, either M or N, and taking the result mod P. All right, so you're taking G to an exponent and taking the result mod P. This is called discrete exponentiation. Recall, of course, that G is an integer. We can think of G as an integer mod P. Okay, now the thing that makes cryptography effective is that for small values of M and N, of course, you can do this easily, but in cryptography, you use enormous values of M and N. And you would think that it might take a long, long time to raise G to the nth power when M is enormous. But in fact, if we've seen in the previous chapter a repeated squaring formula, the first chapter on cryptography. There's a repeated squaring formula. It's in this section 14.3.3. You can go back there and see. And that makes it relatively easy to compute a number to huge exponentials mod a certain integer. So here's a exercise to do this with large numbers, and you can see in that case how things work with large numbers the same way they work with small numbers. Okay, so here's another example with large numbers. All right, so far you've had to take it my word for it that this process is a secret process. So let's see why it's a secret process. So in the process, we took the number G and raised it to an integer. Now, if we wanted to get that integer back again, we would have to do the inverse operation. Now, we've seen inverse operations like this before. For instance, if you take 2 to the third equals 8, if I want to recover the 3 from the 8 and the 2, I have to take the logarithm. Right? If I know 2 to the third is equal to 8, I can get 3 back by taking the log base 2 of 8, and that gives me 3. All right, so you can review your logarithms here. Log base 2 of 2 to the third is equal to 3. Okay, so that gives you the 3 back again. So in fact, the way to recover the exponent is by this operation of discrete logarithm. All right, so you might think that all you have to do to break this secret code is to find discrete logarithms. But in fact, discrete logarithms are not so easy to find. Now, in fact, there's not just one discrete logarithm. There may be several discrete logarithms. When we talked about functions, functions can have inverse only if they're bijection. And in this case, the discrete exponentiation is not always a bijection. So in this exercise, we look at some case where, in fact, the discrete exponentiation is not a bijection, and we don't have a single inverse for each value. So you can take a look at this, how that works out. Okay. Here we say that this phenomenon relate to the one-to-oneness and onto-ness. Okay, and this talks about how, in some cases, the discrete exponential is not a one-to-one onto function. In other words, it's not a bijection. Now, this paragraph talks about how you can guarantee, under what conditions can you guarantee that discrete exponentiation is a bijection. And this is a little bit technical. I'm going to pass by this for now. It relies on some material from chapter 17, which if you haven't had yet, that's a little bit involved. So we'll pass by this for now. But what this says is that in some cases, you can guarantee that this discrete exponentiation function is a bijection, and in that case you can find a unique discrete logarithm that gets you a unique inverse value. Okay? Now, even if you can have a case where there's a single discrete logarithm with a discrete value, it's difficult to compute. So let me go down here and you can see an example of trying to compute a discrete logarithm. Okay. So as it says here, it's easy to calculate 2 to the m and take it mod 11. That's quite easy. We can use our repeated squaring formula. So when m equals 8, you just take 2 to the 8th mod 11 and it works out very nicely. But if you want to invert the process, if you're given that 2 to the m mod 11 is equal to 3, calculate m, how are you going to do that? If I just gave you this information that 2 to the m mod 11 is 3, how are you going to calculate m? Well, it turns out there's no easy way to do this. You can just try. Just keep trying till you get it. All right? 2 to the 1 mod 11 is 2. That doesn't work. 2 to the 2 mod 11 is 4. That doesn't work. You have to go down and try. It's not until the 8th try that you find the right value. So finding this m by trial and error can take a long time, particularly if this modulus is large. If I have a modulus of several hundred billion, then I may have to try several hundred billion calculations in order to find the right one. All right, so that's the key to the success of this Diffie-Hellman key exchange. The fact that if you know 2 to the m mod p, or if you know g to the m mod p, it's still very difficult to find m. It's difficult to invert the discrete exponentiation function. So here's some more problems about solving this. We give you some experience finding m this way by trial and error, and just to see how quickly it gets difficult to find this one. You have to do trial and error many times, and that's how it goes. So I'm going to skip this paragraph for now. Now, one problem with this scheme is you may have someone that doesn't just eavesdrop, but they may modify your message. So let's look down here and see what happens. Suppose this guy Fred, he's in the middle between Moses and Rachel. He's sniffing their internet, and what he does is he's in between the two, and Moses thinks he's sending directly to Rachel, but in fact he's sending through Fred. Fred is changing the information that Moses sends. Fred sets up his own key exchange with Moses. They have a shared key, a symmetric key, that's KM. And Fred sends up another symmetric key with Rachel, and that's KR. All right. So it seems that the Diffie-Hellman key exchange can't prevent this if Fred can put himself in the middle and spoof to Rachel. He spoofs to Moses' communication, and to Moses he spoofs Rachel's communication. So neither one is actually communicating directly. They're communicating through Fred, and he's reading all their mail before he passes it on. Right. Now it turns out that even more magically, there is a way to prevent this from happening as well. So what Moses does is he doesn't just send Q, he sends Q with a signature, and he encrypts it. And if Fred tries to change Q, he ends up messing up the signature. So let me show you kind of how that works, how the digital signature is going to work. So here we have Moses. He has his Q, which is public knowledge, and then we have plus a signature. And then he's going to encrypt that with a private key. All right, now suppose Fred receives this. If Fred receives this, he can decrypt with a public key. Okay, so he knows Q plus the signature. Okay, so you would think that, he can go ahead and change Q and send this off to Rachel. But the problem is, he doesn't have the private key. So he can't encrypt. He can't take this Q and change the signature and encrypt it again. So there's no way that he can send false information to Rachel. He can't do that. So there's no way he can put himself in the middle between Moses and Rachel. So the amazing thing is that Moses and Rachel, having only public communication, non-secret communication, they can still establish a secret link, and no one can mess them up. Now, Fred could prevent Moses from even talking with Rachel, that's true, but he can't spoof Moses. He can't pretend to be Moses because he can't encrypt. He can't change the Q and encrypt it without messing up Moses' signature. So welcome to the wonderful world of encryption, and that's it for this section.